Hello everybody and welcome back. Let's talk about the problem single number. I'm going to explain the binary or the bit-based solution in detail along with the intuitions of how to actually reach to that point of thinking in terms of binary numbers. Let's talk about the problem first. Okay, let's talk about the problem statement. So you were given a non-empty array of integers which they're going to call nums, and every element in that nums array is going to appear twice. So every number will have duplicates except for one particular number. And our goal is to find that single number which appears only once. In other words, that number does not have any duplicates inside of the nums array. Take for example this case over here. Nums equals to 4, 1, 2, 1, 2. 1 appears twice, 2 appears twice, but 4 appears only once. That is why 4 is returned as the answer over here. One more thing to note, and this is the most interesting constraint which makes this problem fun, is that the goal is to implement a solution with linear runtime complexity. So we can't go for n square or n log n or anything like that. We just have to stick to order of n, and we have to use constant extra space. Now, the brute force solution would have been to create a sort of dictionary which would take into account the number as the key and the frequency as the value. And we could go over and iterate over all of these values, creating key value pairs and storing these frequencies, basically creating a frequency table. But that won't work because we have to stick to this constraint of this constant extra space. This is a tricky constraint, and we'll see how to deal with that in just a second. Let's talk about the observations. While I told you early on that I'm going to use a bit-based approach, the first question is, how do we think in terms of bits? How do we arrive, and what are the intuitions behind thinking in terms of binary representations? The first thing we note is the shortage of space. We have to stick to the constraint of order of one space, which means that we can't really store anything of the sort of a dictionary or a set or a list. We have to stick to variables. And these couple of variables that we can use have to somehow compress the information present in the entire nums array down to one single variable. We have to compress the information of nums down to one single variable. How can we do that? Well, one of the things that we should always think about, especially when it comes to problems like these when you have no other way, is to think in terms of binary numbers. It's always to think in terms of these binary representations of these numbers. 2 is the same as 1, 0 in binary. 2 in decimal is the same as 1, 0 in binary. Similarly, 4 is 1, 0, 0, 3 is 1, 1, and 5 is 1, 0, 1. Pretty trivial. And the key point here to note is that we aren't converting these numbers to binary representations. We're just thinking in terms of binary representations. It's a change in perspective here, not in the code. The numbers still remains 2, 4, 3, and 5. Okay, but that's fine. You have the bits. Fine. Bits is fine. What do we do of that? What to do with the bits? Let's put them together. Okay, the first thing we'll note is that, okay, while we do have these bits, the entire goal was to compress this nums into a single variable. Now, can we use this information of bits and do that? We have to do some kind of operation upon these bits. What operation though? Well, you could think in terms of AND, OR, XOR, NOT, or many of these others. One thing that comes out on the top is the XOR operation. This is super helpful when it comes to these kind of problems. Again, if you don't know about it, Google it up. It's super good. It's definitely a thing you should know. Okay, so XOR. Okay, what about XOR? Let's look at a couple of properties of XOR. And I'm assuming you already know about it. I'm just going to do a quick review so that we can understand these example better. So in the case of x XORed with 0, we'll get the answer as x. For x XORed with x itself, we're going to get the answer as 0. Both of these are going to play hand in hand and going to be very interesting later on. Then we also know that XOR is commutative, which means that x XOR y is the same as y XOR x. XOR is also associative, which means that it does not matter what the order of the bracketing is. All of them are going to give the same result. Okay. Let's take an example to understand this better. I'm going to convert all of these numbers to their binary representations. Again, For the computer, it's always binary, and for the humans, it's always going to be numbers. But it's just a change in perspective. There's nothing more. I'm not doing any more lines of code. It's just a change in perspective. We're just thinking about things differently. Okay. If I XOR all of these numbers, I'm going to get the answer as 101, which is the number 5. And that is the answer for this question. 243, 5, 243 has only one single element which has the frequency of 1, which is the element 5. Okay, enough talking. Why does this work? Let's write them all down. 2 XORed with 4, XORed with 3, 5, 2, 4, and 3. That's what we have right now. What can we do of this? Using the commutative property, we can rearrange these numbers however we want, right? So we have this property of x XORed with y gives y XORed x. We can swap these numbers. So one of the things we can do is swap these numbers till we get this kind of arrangement. 2 XORed with 2, 4 XORed with 4, 3 XORed with 3, and then 5. Why is this interesting? That's because if you look at this property over here, it says that x XORed with x will give you 0. A number XORed with itself is going to give you 0, which means that we are going to have these 3 zeros XORed with each other and then 5 that remains at the end. We also know that 0 XORed with 0 is going to give you 0, and that's because of this property over here. This is that any number XORed with 0 is going to give that number itself. Now again, using that, we can see that 0 XORed with 5 is again going to give us 5. And this is indeed the final answer. You can again go ahead and check in terms of binary representations, do calculations, do XOR manually, and you'll find that indeed the answer comes out to be 5. Okay, maybe the code will explain things a bit better, so let's dive into that. We want to XOR all of these numbers. Let's create a XOR variable with the value 0 initially. We want to now iterate over all the num and nums. And for each of these num, I want to XOR it with whatever the previous XOR was. And at the end, we'll return the XOR. In fact, this is the entire solution. Let's do a quick sanity check and submit this. Cool. So we get runtime 128 milliseconds. There is another solution which exists, which is more mathematical, but I wanted to present this because you can use this solution to build up the solution for single number 3. This is single number 1, and you can use this logic to build for the single number 3 solution. Okay, anyway, see you in that video, and yeah, thanks for watching.